Hello, this is the next in the series of testing strategies for the ACS Organic Chemistry final. So this one's going to be all about stereochemistry. So we're dealing with chiral molecules, meso compounds, determining R and S, things like that. So when we're looking at meso compounds, remember these are compounds. They do have to have a chiral center in them, where we have 4 different things hanging off of a carbon. But there is a plane of symmetry. Okay, so if you were to put, say, a mirror image between these guys, it would be the same, right? So for here, right? Notice how there's a nice plane of symmetry. There's a chiral center here and here, right? Because there's there'd be 4 things hanging off of it: the methyl, this hydrogen, this CH2, and that CH, both of those. But notice how if this guy was looking across the mirror, right, you would see the methyl, this hydrogen would see its hydrogen, and so on and so forth. So this one is going to be meso. Okay, this one, if you did that same plane of symmetry, right, there's only 3 bonds shown, so obviously the hydrogen has to be going up, because remember, each bond needs it's usually going to be regular line, wedge and dash. So if you're only seeing the dash, then that hydrogen needs to be on the wedge. So if you're looking across here, across the mirror image, right? So this methyl is going to see the hydrogen. So this is just a regular chiral compound. This one here, right? So you're looking at this, right? You've got a methyl. If you try to do the mirror image across here, then methyl on this side, chlorine on this side, so this is just a regular chiral center. So there's no plane of symmetry on that one. Now this one is interesting because you can slice this molecule like this to get a plane of symmetry. However, it's not meso, and you're like, wait, what? There's no chiral center here. Okay, well think about this. If there'd be a hydrogen here, right? So when you're looking at finding chiral centers, right, you start at here and you go the hydrogen, chlorine, right, CH2, CH2, right? Since this is a tie, then you'd go one more, and voila, we're right back to where obviously these are going to be the same. So this side of the carbon is the same as that side of the carbon. So there's no chiral center here, nor is there one here. And you have to have a chiral center within the molecule in order for it to be meso. So that's our answer there. Okay, so for Newman projections, okay, so this is the most stable configuration of the molecule. Okay, so usually you have to find the most stable configuration. Okay, so usually you're going to be looking between two of these, and notice how we've got these methyl groups hanging off the front. So that's going to be these methyl groups there. This should actually say a 2 on there. Sorry about that. So what we're going to be looking at is this down that carbon. Okay, so let me see if I can make this quickly. So this front. So let's say this is the front. Okay, it's going to have two methyl groups and a hydrogen. Okay, and so this one in the rear, right, is going to have 2 hydrogens and a methyl. Right, so you can just kind of think of it like that: 2 hydrogens, and a methyl. Okay, so first thing you're going to want to do is make sure that they all have this. So this is the front. Obviously, this is the front, and obviously, and the rear is behind. So the way you have to look at these is notice how this carbon here, the front one, right, is obscuring being able to see this one, but we can see the groups coming off of it. Okay, so in this front one, we want to have 2 methyls and a hydrogen. Okay, so this one here has 2 methyls and a hydrogen, 2 methyls and a hydrogen, 2 methyls and a hydrogen, but this one has 3 methyls. Well, that's not good. So that's not actually this molecule, right? So it can't be that one. Now, when you're looking at the most stable configuration, it needs to be staggered. Okay, so these guys have to be sort of these groups have to be in the gaps between these two. Okay, so this one here is eclipsed, where they are right in a line. This is usually how it's drawn, but they're right on top of each other, like see the camera like that. So they're feeling each other here, here, and here. Eclipse is never going to be the most stable, so you can get rid of this. Now, what you need to do then is to look at the gauche interactions. And so that one is if it's a non-hydrogen interacting with something that's not a hydrogen. Right? Hydrogen's small enough that it can sort of hide. But right here you have two gauche interactions right there. But this one, right, this is there's not one there, nor is there one there. But there is only one interaction here, one gauche, because there's two non-hydrogens right next to each other on the staggered configuration. So since we're doing two, this one has two, this one only has one, then this needs to be the most, this is going to be more stable. Okay, so for the Fisher projection, okay, so for these, you have to remember what the bonds are doing, stuff like that. So with the Fisher projection, right, right, I always think it's easier to think about a bow tie, stuff like that. So, right, so these are coming out at you, okay? So what that means is the horizontal is on a wedge like this, and then if it's on a vertical, it's going behind. Okay, so you can kind of see what is it? You can see the bow tie right here. Now this CO2H, remember that is a C double bond O going to an OH like that. It's a carboxylic acid. Okay, so for this one, right? So remember we need to assign priorities based on weight. Okay, so for this one, well, we have an oxygen, carbon, hydrogen, and carbon. Okay, so there's also carbon here. So oxygen's heaviest, so this is going to be our number one priority. Then it's going to be the two carbons. We'll get to those in a second because those are heavier than hydrogen. And then this one is going to be the lowest. Okay, so that's going to be number 4. Now for this one, when you get a tie, you can look at the bonds. So this one has 1 carbon-carbon bond and 3 carbon-hydrogen, or excuse me, one carbon-carbon and 3 carbon-oxygen bonds, right? So 1, 2, and then this one here. This one right here has, so that carbon there has 2 carbon-carbon bonds, right here and right here, 1 carbon-hydrogen, okay, and 1 carbon-oxygen, right? So the heaviest bond in both of them is carbon-oxygen, but this one has 3 of them. So this is going to be the higher priority, so 3 like this. So it looks like 2, 1, 3, 4. Now, most people I know do the what is it? The steering wheel method. I'll show you another one in a minute. But that's what seems like most people get taught. Okay, so we're going to say, right, we're going to have it go like this. So this is our, right, so number 1 is going to be red. This is going to be blue. Oops, maybe it's blue. This is green. And then this is that's our hydrogen. Okay, so what we need to do is we need to get this guy behind. Okay, so we're just going to rotate it like this, and as we're rotating around, okay, right, so our red is over here, so well, our 4 is back here, so our red has gone over to this side. Okay, so this is number 1. The green is now over here, so that's our 2, and then our blue is 3 down here. So all we really did is just rotate this blue. So this is 3. So we're going clockwise with 4 going behind like this, and so this is going to be R. There's a bunch of different ways that you can do it. This is probably the most common. The one that I was taught was with the hands, and what you do is you point your thumb for wherever 4 is pointing. Okay, and so 4 is pointing that way, so I'm going to put my thumb this way, and so your fingers are going to sweep. Your fingertips are going to sweep 1, 2, 3, and since I'm sweeping with my right hand, so going from 1 to 2 down to here, right? So you're going to sweep like that. So like this, with the 4 pointing, with your thumb pointing this way, right? Since I can sweep with my right hand, it's going to be R. Okay. If I try to sweep it with my left hand, right, because the 4 is pointed that way, so you go 1, 2, ow, you can't do it. Okay. If it swept with your left hand, it would be the S, the sinister one. Stuff like that. So this is nice because you don't have to rotate it in space. You just have to rotate your wrist. But it's a little bit more complicated because you need to get your fingertips. Now, also don't forget that you can rotate your picture here. But either way, there's some other different ways of doing it, but those are the two that I usually talk about. But do whatever works for you. So we know that this one here, so this is carbon 1, carbon 2, carbon 3, carbon 4. So at carbon 2, it's going to be the R. So we can get rid of these two. So now we just need to figure out this guy. This one here. So here we've got a carbon, oxygen, hydrogen. Right? So this is going to be 4. Right? This is going to be 1. Okay. So this one right here has, right. So this is a tie here to here. Okay. This one has. Right, 1 carbon bond, right? 1 carbon oxygen and 2 carbon hydrogen. This guy here has has 2 carbon, 1 carbon hydrogen, and 1 carbon oxygen. Now this one, they both have 1 carbon oxygen bond here, but this one up top has 2 carbon, while this one only has 1. So this one is actually going to be. So if we do 1, 2, 4, sorry, 2, 3, okay. So now it's 2, 3, and then 1, 4. Okay, so notice how you don't even have to go through actually assigning this. Notice how the 2 and the 3 are the same, but we flipped 1 and 4. So that means we flipped the when you flip what's on the wedge and dash, or two things, you're going to flip the stereo from R to S, or S to R. So since we flipped 1, now this has to be S. We don't even have to go through the whole rotating or anything else like that. So we know that it's actually going to be this. Okay. What's the relationship between these two molecules? Okay, so you have 2 chiral centers. They're here on each one of these molecules. Right, so if right, and all the things are connected to the same carbons. Okay, so in order for the and to be an answer, is all the wedges and dashes all have to be flipped, all flipped, even if it's just 1, all flipped. If not all have been flipped, then they're diastereomers. Okay, so this one is held fixed, and this one is. This one has been flipped, so not all, so it has to be this. To be constitutional isomers, okay, they would have, it would be, say, if you were comparing this one to, say, this. That would be a constitutional isomer. That still has the same formula, but the connections are going to be different. The same molecule, right, would have to have this be as a wedge. Okay, if it's a dash, it's going to be actually an enantiomer. But anyway, so it's going to be B. How many total possible stereoisomers are there in 2,4-dibromopentane? Okay, so draw this out. You can go ahead and do this, right? So here's your pentane. I usually like putting dots in to show where the carbons are. And so dibromopentane, so 1, 2. So we've got a bromine here, and then a bromine here. And you say, okay, well, how many chiral centers do we have? So, right, so if you draw on our hydrogens, it's a little easier if you draw them like this. So methyl, so CH3, bromine, hydrogen, CH2. Those are 4 different things. So there's a chiral center here. And then there would also be one here, right? Bromine, methyl, hydrogen, CH2. So there's 1 right there. And you say, oh, well, you know, it's 2 to the n, right? So it would be 2 to the 2. So it would be 4. That's not right. And they trick you because notice how there's a plane of symmetry here. This is the max. It doesn't necessarily mean how many your molecule is going to have. Because there's a plane of symmetry here, you can have the issue of you can have an issue of meso compounds. Okay, so if you had, say, two wedges, and you don't have to go through this, but if you have a plane of symmetry in the molecule, you got to be careful. So this, so bromine, right? And so here, so these are the 4 possibilities. Oops. Okay, so these guys here, these are enantiomers, okay, and they're diastereomers, stuff like that. But if you notice these guys here, if I were to take this molecule and flip it over here, it's the same. So these are the same molecule. Because these 2 guys are meso, they're actually the same molecule. So in fact, you really only have 3. So this is a good thing to say, like, okay, yeah, it's 2 to the 4th. You're thinking 4 because there's 2 stereocenters, but you have to be careful about this plane of symmetry. If you have a plane of symmetry, you're going to have meso, and you're going to start knocking some out. So be careful. Now for this one, was the stereochemical relationship between these 2 molecules? This one you don't even have to look at it, right? All the information you need is right here, right? So when you flip wedges and dashes, right, you flip from R to S and S to R. Okay, so if this is, so the same rules apply as the other one, right? Enantiomers, right, all flipped. Diastereomers, not all. Okay, so with that, so obviously they're more than constitutional isomers, right? Because their names are exactly the same, except for the R and the S. Okay, they're not the same molecule, right? Because this is SR and this is SS, so it can't be this, can't be this. Okay, so the question is, did we flip them all or not? So we're going from S to S. Okay, so that's the same. But here it's R to S. We've only flipped 1. Okay, so we didn't flip them all, right? So we did not this one. So that means they're diastereomers. You don't have to draw it. You don't have to do any of that stuff. Just look at the R and the S. Now, which one of these is optically active? Or chiral. So the deal with this is that, right, so you have to have chiral centers. So, chiral center, but not meso, because a meso compound is not optically active. All that means is that it can rotate that plane polarized light. So even though they'll have chiral centers, it's not a meso. Okay, that's what it means. So here, right, there's no plane of symmetry in this molecule, right? You had OH on this side, methyl on here, so this is definitely going to be, and there's a chiral center here, right? Because if you had OH, H, right, so you had CH2, CH2, well, that's a tie, but you can still go to here, and this is a CH2, CH, right? So right here, it would be, they're different. So this side of the ring is different from that side of the ring. So that means that there's at least 1 chiral center here, and it's right here. There's also 1 right there. So this one's optically active. Okay. Now this one here. Oh well, here let's do this one here first. Okay. So this one here, right? So you had chlorine, hydrogen. Right, so remember we need the 4 different things hanging off it, right? So here's a CH2, CH2. So obviously you can't have chiral centers there, and CH3, CH3. Now we're at the end of our chain, right? So there's no chiral center here, so you can't be optically active. So this one is not. Okay. Now here you'd say, oh well, hey, there's this isopropyl group, a hydrogen, an ethyl group, right, and a set of lone pairs, right? Lone pairs can be a thing of the 4, but this is an exception, right? So what happens is this nitrogen's the one where this thing will actually flip back and forth, okay? And because it'll do that, in order to be optically active, it's got to be fixed. So even though this has 4 things around it, it's one of those weird exceptions that they love to throw on the test, where this actually is not optically active, because this chiral center can't stay fixed, because these lone pairs will tunnel through the nitrogen and you get this flipping effect, unless you're going to run it at cryogenic temperatures, you're not going to be able to do this. Okay, so that is actually not, even though it has a pseudo chiral center. Well, it does have a chiral center. This one here, right? Again, we have our four things, right? We have an ethyl group, an oxygen, a chlorine, and a acetylone pairs. Okay, but it's not a nitrogen here, so this is good. So actually, it's just these two that are optically active. Okay. Okay. Now for this one, which would create a product that has a meso configuration, right? So it has that plane of symmetry. So really, all this is asking for is syn versus anti addition of the product. That's really what it's asking for. So if the reagent goes on the same side, right, with syn addition, then it could create a meso product. If it's not, then it won't. If it goes on anti, then you won't be. So for here, this is hydrogenation, and so what you would end up with is these are deuteriums, so this is heavy hydrogen. So it's different than regular hydrogen, but remember with hydrogenation, the hydrogens end up on a surface, and then you sort of come in and go like that to get them out, and so they're going to end up being on that same side. So that means the deuteriums are going to be on the same side. There's a nice plane of symmetry here, so this is going to be so that one's going to be meso. Okay, so this one's meso. So for this one, right? So you're adding chlorines across here. So remember, in this mechanism, you have to go through this. It's the chlorine version of bromonium ion. Oops. Right. Right, and so you end up with this. This is going to block the one of the faces, and so when the chlorine comes in, it's going to go there, right? So you're going to end up with the chlorine and chlorine. So this is anti addition. So this is not. That's not going to give a meso product. Okay. So for this one, you're going to say, oh well, hey, we're doing oxymercuration, right? Because we got the mercury here. So with that, so we're going to add the OH on the more substituted side, the higher ordered side. So this side is tertiary. This, right? So this is tertiary. This side is is secondary, right? So the OH is going to go there. So the product that you're going to get, right, at the end is going to have a methyl and an OH. Now the thing is, the way this molecule is put together, this actually is not a chiral center, right? Because it's the same thing, right? CH2, 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 and then it comes back in. So there's no chiral center. So no chiral center, you can't be meso. So it's not going to be that one. Now for this one, the osmium tetroxide. So remember with this one, the osmium comes down and sits on the same side, right? So the intermediate is this, right? So or something like that. But the oxygens here, they're going to end up, you're going to be putting on the OHs on the same side. So this is, you end up getting syn addition, right? So your product ends up like this, right? So you're going to get this one too. So it's just these two that give meso products. So really, you have to look for the syn versus anti, or if there's going to be a chiral product. Now for this one, which of the following molecules is the enantiomer of this molecule? So you're looking for the enantiomers. So if this is R, then we want to find the S version. Okay. So before we do anything, right? Notice how these three ones here have this part fixed. Okay. It's just these that are changed. So if you've just rotated it, okay, then it's going to be the same configuration. Okay, so here, right, the methyl group has come down here. So in this particular case, the methyl group has come down here. The OH is on here, and then the hydrogen has gone here. So really, all we've done is rotated this 120 degrees. So this is going to be the same. So it can't be this one. For this one, right? Again, what we've done is we've rotated it back, right? So the oxygen has, the OH group has come up here, the hydrogen is coming over there, and then the methyl group has slid down here. So again, this is going to be whatever that configuration is. So on here, right, here the methyl is fixed, right, and then we've flipped these two. Okay, and so it's going to be that, right? We've only flipped 2 sets of bonds, right? The other 2 are held fixed, so that's automatically going to be it. Notice how we solved this problem. We didn't even have to look at that one if we knew that it would be this one. So that we just need to take a look at this. We didn't have to figure out R and S. We just need to do the which bonds are flipped. Okay. Now, how many chiral centers are present in the following molecule? Now, this is one of those ones where you want to draw the hydrogens, draw the H's in, draw those CH bonds. Okay. So for here, right? So this will be a CH2 because two bonds are shown. Same here, CH2. Here 3 bonds are shown on this one, so there's a hydrogen here. This one 2 bonds are shown, so CH2. Here on this one, right, 1, 2, 3 bonds are shown, so it's a hydrogen. Same thing up here, hydrogen. Here 3 bonds are shown, so there's a hydrogen here. This is a methyl, right, so CH3. And then finally here, right, there's 3 bonds shown, so there's a hydrogen. So we can knock out, so it has to have 4 different things hanging off of it, okay? And so this one, oh, this is a carbon here. So we can knock out this one, we can knock out that oxygen, we can knock out that carbon because it only has 3 things hanging off it, this CH2, this CH, and this O. Okay, so we can knock that guy out. Well, this one might, right, because has 4 different, that at least looks promising. This CH2, we can get rid of that. That's not going to be it. So here, again, this only has 3 different things hanging off, this carbon, and then hydrogen. So both of these are out. The methyl is out. But what about this? Okay. So for here, right, so again, we're going to be looking for 4 different things. So we're going to have, right, a hydrogen, an oxygen, a CH, and a CH. Okay, well, so we have this, and then here versus here. Now here, it wouldn't necessarily make much difference which way you went, right? But if you're going to, right, but we need to go out 1, right? So this has a carbon-carbon double bond, and here is a carbon-oxygen double bonds. So that means this is a chiral center because we can kind of keep going around this ring and find differences. Okay. Same thing with this one, right? We have a CH2, we have a CH, we have an H, and we have a this C double bond O here, right? So there's a chiral center here. Now for this one, right, we have a CH3, we have a CH, we have a CH that's part of a double bond, and then we have an H. Again, we're going to have, so we have 4 different things hanging off of that carbon. So we have 1, 2, 3. So with that, so we have 3 chiral centers of the molecule. Okay?